All right, so let's get going on today's class. So what we're going to be doing today is we're going to very briefly, for this day only, take a look at Chapter 6. And Chapter 6 is where the textbook will move us from dealing with individuals, sample sizes of 1, to sample sizes greater than 1. So we're not going to spend a lot of time on this chapter because we've been doing this the entire time. This is one of the areas where I disagree with the textbook, where I believe that they should have been doing this from the beginning. So that's what we've been doing. So this will serve as a type of almost review, but it will definitely give us the final piece that we need in order to do that 5-step procedure. Now, before I get to that, just very quickly, forgot about announcing the next step in the social media development. So let me pull that up, and I'll talk about that a little bit, just so that we are all ready to go. All right, so before we launch into our work today, our statistical stuff, the next step for the social media professional development, step number 5, details about that. So what we have for this is now what we're going to start working on is developing your brand. So we've been doing some amplification, we've been plugging into that network. We've been helping others by amplifying their voices through retweets, and now it's time to develop your own brand, make sure that your social media presence has a theme to it. And the way that we're going to do that is to make sure that the things that you tweet about have something to do with the area of psychology that you're interested in. So we are going to, this week, tweet 3 articles about any area in psychology that you are passionate about. The area in psychology that interests you, the area in psychology where if you were to have a career in psychology, that would be the area that you go into. 3 articles from the internet that are about that particular area. So for example, I work in the psychology of art. So examples of articles, and we're not talking about hardcore primary research journal articles that you need a subscription in order to access. We're talking about psychology articles that have been published in mainstream outlets. So ones that you can access just through a Google search. So for example, here there was an article, New Study Offers Clues to the Dominance of Curved-Filled Museum Designs. So that's about the psychology of art. That's about why designers love curves in their architecture, but actual people do not like curves in their architecture. And then there was another article on an empiricist on art that basically looked at how can we study art through an empirical experimental method. And then the last one, do you like dogs playing poker? Science would like to know why. So why is it that some art is very popular, other art is not popular? And especially in something like dogs playing poker, where critics disagree on whether it's high quality, but just about every single American family at one point had a picture of this somewhere in their home. So again, a big reason people favor an artist's work over an identical copy is their belief that some essence of the artist is left behind in the original. So psychology, again, is studying the art of, or the science of, why we have these aesthetic experiences, and that's my area. So this would be an example of 3 articles that I would tweet because it's consistent with the brand that I've developed in my Twitter feed. So for this step, we're going to use the hashtag MyPsychArea2019. So on your 3 retweets, just make sure that you have that hashtag. It's the only thing that you need to write. If you want to add a comment, again, make sure that you look over that article about what to write and what not to write. But do make sure that you have that hashtag. That's how we're going to be tracking this. And this is going to be due Monday, November 4th, so this coming Monday by midnight.
Is there a screenshot of the article?
No, so the way that you would do it is you would actually, most articles have a feature where you can share them to your Twitter account. If not, you would just copy the URL and then share that. So basically it's a way that, it works in a way that when people see your tweet, if they're interested in that particular article, they can just click on the link in your tweet and go directly to the article.
Hashtag MySiteGary 2019, was that what it was?
MySiteGary 2019, yep. All right, any other questions on the next step? All right. So now that we've taken care of that, back to the statistics at hand. And there we are. Okay, so once again, we are almost to the point where you're going to have the complete package in terms of analyzing hypothesis tests. You're going to have the complete package that's going to allow you to go from 14 subjects that you directly measured and be able to say things about the entire, there we go, population of individuals that you're interested in. So not just the 14 autistic students that you treated, but you can then say things about the entire population of autistic children and find a way to help them, to treat them. And again, this is all part of that super cool aspect of statistics that's going to allow us to make psychology much more powerful than it would be on its own. This is getting to the point where we are now delving into the actual professional procedures that psychologists use when they're analyzing their data. And basically, if you extend the metaphor of the statistician in psychology as a ninja, we are almost done with your ninja training. We're almost ready to let you out there into the real world. Basically, you are almost ready to do this alone. But out of those 5-step procedure that we've been working on, right now, currently, you have 4 out of the 5 steps. So you can do step 1. You can do a null and research hypothesis for one-tailed and two-tailed. You have that ability. You can do step 3, which is determining your cutoff scores on your comparison distribution. You can do step 4, where you determine where your sample is on your comparison distribution. And then you can do step 5, where you decide whether or not to accept or reject the null hypothesis. The only step that you couldn't do was step number 2, which is determining the characteristics of the comparison distribution. That's the step that we're going to fill in today. That is the final piece, and that's what we're going to be working on and looking at in today's class. So we are going to once again revisit the idea of samples and populations. Just to, one more time, make sure that that distinction, that important distinction is clear in our minds. We're going to revisit the distribution of sample means, and because that is your comparison distribution. And then we're going to see how to determine the characteristics of that distribution of sample means. How do you use that central limit theorem to determine what is the mean for your distribution of sample means? What is the standard deviation of your distribution of sample means? Basically, what are the characteristics of your comparison distribution? And then we'll have a very quick little in-class demo of that, just to make sure that we're all on the same page. All right, so once again, in this 5-step procedure that we've been using, up until now, we have that unsatisfying message that we're going to see how to determine the characteristics of the comparison distribution. We're going to see how to do step 2 in the next chapter. But for the time being, it needed to be given to you. Well, today is when we finally get to that next chapter. Chapter 6 is where you learn how to get this mean and standard deviation of the comparison distribution. How do you figure out this information so you have the complete 5-step hypothesis testing package? So all of this goes back to the idea of samples and populations and the relationship between samples and populations. So samples are used to estimate population parameters, and that's the basic of a hypothesis test. We're taking a look at our sample and we're asking, does the treatment that we apply to our sample work for a population. We're trying to estimate, what will this treatment do based on what it did for the sample? What will it do to the population? So that's the basis of what we're doing here. And as we saw before, the challenge in using a sample to estimate a population is that you're never really sure where your sample came from for a particular population. So for example, if we wanted to estimate the mean of this population here, we might start by saying, all right, well, let's take a sample from that population. And if we got a sample that was evenly distributed throughout the population, some of the subjects came from below the mean, some of the subjects came from above the mean. If we had that particular sample, our sample mean would equal our population mean. We would correctly estimate our our population mean based on what our sample mean was. On the other hand, though, it's also possible that we would have a sample that vastly underestimated what that population mean was. We could have a sample that came from the low end. All of the subjects came from the low end of the population, in which case our sample mean, correctly calculated, would be much lower than our population mean. We would underestimate our population mean, and at the same time we might go the other way. And we might end up with a sample that comes from the extreme high scores in the population. Once again, we could calculate that sample mean correctly, but now we would overestimate the population mean. So the basis of hypothesis testing is taking a sample that has a certain mean and determining how unlikely is it to get a sample with that mean from your population. How unlikely is it to end up with a sample this extreme coming from that population? That's the essence of that hypothesis test. Because if this sample is very likely to have come from the population, then we say that its extreme scores are just due to random variation. But if this sample is highly unlikely to come from that population, if you have to get subjects that are really extreme in order to get a sample this high of a score, then we say, well, it's highly unlikely that it could have come from this population. It must have that extreme score because of the treatment. And that's how you decide between whether a treatment is effective or whether it's not effective. So all of that depends upon that distribution of sample means. All of that depends upon us being able to figure out how likely is it that we could get a sample like this from a population like that. So that distribution of sample means, we've seen this before. By way of review, we'll take a look at it one more time. But remember that this distribution of sample means is your comparison distribution. This distribution is what you're looking for in step 2. Because it's called the comparison distribution because you have your sample and you want to compare your sample to a distribution of samples, right? You can't compare your sample to a distribution of individuals. That's not fair. You want to compare your sample to a distribution of samples. You want to compare your sample mean to a distribution of sample means. So that's why the distribution of sample means is the comparison distribution that we're going to be working with. And the theoretical way to think about it is that your distribution of sample means is made up of every single possible sample that could be taken from your population. And every single possible sample will tell you how unlikely any single sample is from your population. So that's why that idea of having every single possible sample in a distribution is so useful, because you can then compare your sample and see how extreme or how unextreme your sample was. And importantly, and this is the one key thing where when students make an error on step 2, this is the error that they make. They forget that the comparison distribution does not equal your population distribution, which means that the characteristics of your comparison distribution do not equal your population distribution. And the only time that it does equal your population distribution is when your sample distribution is based on sample sizes of 1. So if you're dealing with a case study, and only with a case study, if you're dealing with an experiment that has a sample size of 1, that's the only time that your population distribution is going to look like your distribution of sample means. That's the only time. Any other sample size, for example, a sample size of 2, this population distribution is not going to be the same as the distribution of sample means. So as soon as you have 2 subjects, your distribution of sample means is not the same as your population distribution. And you now have to figure out what is your distribution of sample means. And one easy way to remember this is that your distribution of sample means becomes more and more like a normal distribution the higher your sample size is. So the very fact that you're taking it from the same population, but depending upon the size of your sample, your distribution of sample means changes its shape, is another clue that it is not the same as your population distribution. So this is what the distribution of sample means will look like for dice rolls when you have a sample size of 2. This is what it'll look like when you have a sample size of 3. This is what it looks like when you have a sample size of 4. And importantly, it changes. It becomes more and more normal. This is what it looks like when you have a sample size of 5. And this is what allows us to calculate how unlikely a certain sample is. This is what allows us to calculate this distribution of sample means, how unlikely our sample is to have occurred. So for example, if you were going to get a roll of 5 6s, right? There's only one way to get a roll of 5 6s. You have to get a 6, a 6, a 6, a 6, and a 6. There's only one way to get an average of 6 from a sample of 5 dice. You have to roll 5 6s. We can calculate what is the proportion of this bar here compared to the rest of the distribution. And you would find that the probability of rolling 5 6s on one roll is something like 1 in, I don't know, probably like 10,000. I'm just estimating right now. Highly, highly unlikely. Which means that if you were playing somebody in a dice game and they rolled 5 6s when they needed 5 6s, you can be pretty confident that the dice are rigged rather than they just got that extreme sample. That's again the basis of hypothesis testing. All right, so we have that distribution of sample means, and we built this up in our previous analyses by taking a look at all the samples, all the possible samples from a population, but usually you only have the one sample. Usually you're only dealing with one sample of 12 subjects, one sample of 20 subjects. So how do you actually figure out this distribution of sample means? And that is where we go back to the central limit theorem. So the central limit theorem is how you do step 2. The central limit theorem tells you everything you need to know about how to do that second step. And what it says is that for any population will have a population distribution. That population distribution will have a mean of mu and a standard deviation of sigma. Right? So any population has a mean and a standard deviation. Based on that mean and standard deviation, your distribution of sample means, your comparison distribution, will have the following characteristics. It'll have a mean of mu. It'll have the same mean as your population, but importantly, it'll have a smaller standard deviation. It'll have a standard deviation that is the standard deviation of the population divided by the square root of the size of your sample. And that's why, as sample size increased, you could see the distribution of sample means squeezing in. You could see the extreme scores getting smaller and smaller and less likely because that standard deviation was shrinking as sample size increased. And then the last little bit of the distribution of sample means, the central limit theorem, tells us that as the size of your sample approaches infinity, the shape of your comparison distribution will approach a normal curve. So it doesn't matter what your population looks like, as you get a larger and larger sample, your distribution of sample means will come closer and closer to an actual normal curve. So once again, to illustrate these points, so there's your population distribution, there's your distribution of sample means. And in this population distribution and distribution of sample means, the mean, the balance point, is right at 3.5. So for dice rolls, the population mean for every single dice roll of a six-sided dice that has ever occurred is 3.5. For a sample size of 1, the distribution of sample means has a mean of 3.5. So notice that the mean of your comparison distribution equals the mean of your population distribution. That's point number 1. Point number 2 is that as this sample size increases, the standard deviation, the spread of your comparison distribution shrinks. It gets divided by the square root of the size of your sample. So as the size of your sample goes up, the standard deviation of your comparison distribution goes down. And you can see that. So when it's a sample size of 1, look how much is over here in the extreme scores. Look how many 1s and 2s we have and how many 5s and 6s we have. We have a lot of spread in our comparison distribution. As soon as we go to a sample size of 2, look how few means there are with 1s and 2s. Look how few means there are with 5s and 6s. Our distribution got squeezed. It got squeezed in towards the center because the standard deviation of our distribution, the spread of it, has decreased. You increase it even more to a sample size of 3. Now look how few 1s and 2s there are. Now look how few 5s and 6s there are. Most of your distribution is now in the middle. Notice that your mean hasn't changed. Your mean is still right there, 3.5. It hasn't moved. But your spread has moved. And lastly, as that spread is decreasing, as more and more of your distribution is getting squeezed in to the center, your distribution is looking more and more like a normal distribution. And those are the 3 parts of that central limit theorem. Those are the 3 parts of figuring out your comparison distribution. So once more, it doesn't matter what your mean is. It doesn't matter what your population looks like. Your distribution of sample means will have the same mean as your population distribution always. But as that sample size increases, your distribution of sample means is going to get squeezed compared to your population distribution, with more and more of the means coming in close to the center of the distribution. But importantly, it's going to look more and more like a normal curve. And that's why we can use Appendix A1, because we know that as soon as we have a sample, we're dealing with a normal comparison distribution. So we can look up values on a table that has the values for a normal distribution. And then finally, just one more time, if we have this distribution here, once again, your distribution of sample means will have the same distribution, the same mean as your population distribution, but its standard deviation gets squeezed in as your as your sample size increases, and that can be seen by fewer extreme scores and more central scores. And importantly, it starts to look more and more like a normal distribution as you go from 2 to 3 to 4 to 5 subjects in your sample size. All right, so just one more time on the central limit theorem. First off, thankfully, it applies to any population. So that means that there is no population in psychology that is off limits. There is no population that you cannot analyze with statistics, because this central limit theorem will work for any population. Any population will have a mean and a standard deviation, and you can figure out the distribution of sample means. You can figure out that comparison distribution, step 2, by just grabbing the mean of the population and taking the standard deviation of the population and dividing it by the square root of the size of your sample, and then as that sample size increases, your distribution of sample means, your step 2 comparison distribution, will get closer and closer to a normal curve. All right, so any questions on that so far? Okay. So just to make it explicit, just to do this one more time, and this time we'll phrase it the way that your textbook has phrased it. So if when you're reviewing, you don't get confused because they do use it. They do use terminology that's slightly different. According to their version of the central limit theorem, there's 3 rules for determining the characteristic of your distribution of sample means, your comparison distribution. Rule number 1 is that the mean of your distribution of sample means, the mean of your distribution, your comparison distribution, is the same as the population of individuals. So this one is not going to trip you up because the population mean is the same, the mean, this is why I don't like the way the textbook did, this is why we're doing this right now. This is what it stands for. This is the your distribution of sample means, mean. This is your comparison distribution mean. That's going to equal your population mean. So whatever your population distribution mean is, that's the same as your comparison distribution's mean. So in step 2, you can graph your population mean and you don't have to do anything with it because your comparison distribution has the same mean. This is the easiest step. The step that is the one that you got to watch out for is rule number 2, and that has to do with the variance or the standard deviation of your comparison distribution. And that is not the same as the standard deviation of your population. And this is where, if you make an error on these calculations, 95% of the errors come in this step. So when I grade students' exams and they don't get perfect on their hypothesis tests, most of the time it's step number 2, where they got the variance or the standard deviation incorrect. So they have the variance in there, but we don't usually use the variance. So we're going to not spend too much time on here. We're going to take a look at the standard deviation, which is what we normally use. So the standard deviation of your comparison distribution, the book calls it population standard deviation of the distribution of comparison means. This is why I put this up here. It's kind of confusing. That is this. That is the standard deviation of your comparison distribution. And the standard deviation of your comparison distribution equals the standard deviation of your population divided by the square root of the size of your sample. And again, the most common error in this early stage of hypothesis testing is forgetting to divide by that square root of the size of your sample. Forgetting to take that information and squeeze your population standard deviation so that it's the standard deviation of your comparison distribution. So this is completely understandable because up until now in your homework, in your pretest and your post-test, they've been giving you examples with one subject. We have one score. We took a look at one individual. And when you take a look at one individual, you can compare it to the population because that's a population of individuals. Now that you have a sample, you have to compare it to a distribution of samples. You have to do this step. And if you don't, your hypothesis test could come out incorrect. So make sure that you do this step right here. Take the standard deviation of the population and divide it by the square root of the size of your sample. And incidentally, this move right here is why psychologists always want bigger samples. They always want as large of a sample as they can possibly get, because the larger your sample, the more powerful your comparison distribution is. So let's say that you have a population, and let's say that that population's standard deviation is equal to 100. All right, so that's your population. And we won't worry about the mean, but let's say that your population standard deviation is equal to 100. And you want a comparison distribution. So this is your comparison distribution right here. basically, your ability to detect small differences in a hypothesis test is directly related to how squeezed in your comparison distribution is. So we don't want a lot of variance. We want a very small standard deviation for your comparison distribution. The smaller this is, the more powerful your hypothesis test is. So this is why psychologists always want larger and larger samples. Because if we have a sample size of 25, right? If we have a sample size of 25, then this standard error right here is going to equal 100 divided by the square root of 25. That's 100 divided by 5. That gives us a standard deviation of 20. So we've squeezed it in. We've squeezed it in from 100 to 20. So we're going to be more able to detect differences in our experiment. That's with a sample size of 25. Let's say that we take that to a sample size of 100. Now our comparison distribution has the standard deviation of 100 from our population divided by, not the square root of 25, the square root of 100. And the square root of 100 is 10. And 100 divided by 10 is not 20 the way it was. Now it's a standard deviation of 10. So by increasing the number of subjects, we've squeezed in our comparison distribution, making our experiment more powerful because our comparison distribution has a smaller standard deviation. And that's why higher subject sizes, larger subject sizes are always welcomed by psychologists because it makes your experiment more able to detect those small little differences. And none of that is possible without that move right there. So do not forget this, right? Remember it any way that you can. Remember the fact that the comparison distribution is getting squeezed in, so we have to do something with the standard deviation of the population. Remember that psychologists always want larger sample sizes, so we got to be doing something with the sample size. Remember it any way that you can because it is the most common error forgetting to do that move right there. All right, and just as to complete the analysis, this, I've been calling it the standard deviation of the comparison distribution. This is so important in hypothesis testing, it gets its own name. So this is actually called the standard error. The standard error is exactly the same as the standard deviation of your comparison distribution. They're the same thing. It's just a lot easier to say standard error. So that should give you an indication of how important this is. Because not only does it get its own term, they've actually changed the name of it. It gets its own name because it is so vitally important. And you will see this everywhere in hypothesis testing where they will report the standard error and they'll talk about the standard error. What they're talking about is that spread of your comparison distribution, standard deviation of your comparison distribution. All right, and then the last one is, or the last rule, is that the shape of your distribution is going to be approximately normal if your sample size is 30 or more, and that's just an arbitrary number that your statistics textbook has decided upon. So it'll be different, the number of different people that you ask, but that's the one that they use, so we'll use that cutoff. It's 30 or more, will ensure that you have a normal distribution, or if your population started normal to begin with. So some population distributions are normal, and their comparison distribution is going to be a normal shape, regardless of the size of your population. However, most populations, we don't know what their distribution is, so we make sure that our sample size is large enough so that whatever our population looks like, our comparison distribution, because of that squeezing in for the standard deviation, is going to look like a normal distribution. All right, so any questions on that before we crunch some numbers? Okay, so if you haven't already, I suggest you follow along in Canvas, week 10, class 1, practice chapter 6, hypothesis test with means of samples. And what we're going to do with this is just to illustrate exactly what I was talking about up until this point, which is it kind of looks a little weird here, which is the issue of, let me zoom to this so we can actually see this. All right, so this is the issue of that comparison distribution, figuring out that comparison distribution. So we've already seen these examples. We're going to take one more look at them. We're not going to do the hypothesis test. We're just going to do step number 2. All right, so let's give it another shot. This was example number 2 that we had in our initial hypothesis testing. Comparison distribution, once again, needed to be given to you. But let's once more now try to see where those numbers actually came from. So once again, you would read the description. And this one is about placing children in timeout can be an effective form of punishment. In the study, participants were shown a series of colored shapes and had to classify each stimulus into 1 or 2 categories. Each correct response was rewarded with a nickel, and each incorrect response was punished by a timeout period of 10 seconds. During the timeout, no stimulus was presented, and participants had no opportunity to earn more nickels. So the population of adults completing the task with no timeout penalty have a mean accuracy of 76.1% with a standard deviation of 6. A sample of 9 participants completing the task using a 10-second timeout penalty have a mean accuracy of 79.1. Do the data indicate that the timeout procedure changes accuracy? So if that was a hypothesis test, and we're looking to do step 2 here, again, what we need to do is we need to find, first off, our population mean. What is the mean? Not for the sample, not the treated sample, but for the population that this sample came from. So the population of adults, it mentions right here, has a mean of 76.1%. So we put in 76.1% into our population mean, and lo and behold, immediately, the comparison distribution has a mean of 76.1%. Again, the comparison distribution mean is the same as your population mean. This time, though, we have our population standard deviation, and we see that, and it's a standard deviation of 6. So once again, you will find that information. It will say your population standard deviation is, and it'll give you that information. For your comparison distribution, however, you need the population standard deviation divided by the square root of the size of your sample. So somewhere in here is information about how many subjects were in this experiment, and we get that information right here. So it says a sample of 9 participants, n equals 9 participants completed the task. That means that our sample size is 9. We pop that in, and this time it worked out right. This time I had the math correct from the beginning. We have a standard deviation for our comparison distribution of 2. So that matches the information that we had before, and that's where we got this information from when it was given to you. From the population and the size of the sample, we determined that the standard deviation was 2. Population standard deviation, 6. So again, the standard deviation of your comparison distribution will not be the same as your population's standard deviation. All right, and one more just to complete this look here. So this was from the example that we did for the exam review, I believe it was. So we have psychologists wonder if exposure to social media in early childhood predicts lower depression in later childhood. Suppose a psychologist tests 40 teenagers who are high social media users in early childhood. The mean back suppression inventory BDI score for this sample is 14.1. The back suppression inventory scores to the general population have a mean of 15 with a standard deviation of 2. Because the sample size is 40, the comparison distribution has a mean of 15 and a standard deviation of 0.32. So once again, where did we get that information? Well, it starts off with your population mean and your population standard deviation. So once again, we look for that information in the question. It goes, the Beck's depression inventory scores for the general population have a mean of 15. So we pop that in. Whoops. And it has a standard deviation of 2. So we have that information here for our population mean and our population standard deviation. Our comparison distribution mean has the same mean as our population mean. So that again is the easy step to do. Our comparison distribution standard deviation is your population standard deviation divided by the square root of the size of your sample. So the last piece of information you need is how big is your sample. And in this case, it says that your sample size is 40. 40 teenagers were studied. Your sample size is 40. We pop in 40, and 2 divided by the square root of 40 gives us that 0.32 that we saw for the standard deviation. So if I can get my Excel to work, there we go. That 0.32, that's where we got that comparison distribution standard deviation. Okay, so hopefully the first failure here did not distract too much for the overall message of this, which is that you need to do this step here. You need to take your population standard deviation and you need to divide it by the square root of the size of your sample. So make sure that you're gathering all that information from somewhere in your question. What does your population mean? What is your population standard deviation? And what is the size of the sample that you're using? You'll need all of those to calculate your comparison distribution characteristics, and especially be careful with your comparison distribution standard deviation where it is not the same as your population distribution. All right, so let's wrap up our look here at this chapter 6. So again, we're not going to spend a lot of time on chapter 6. This is the only class that we are going to devote entirely to chapter 6. But we will be using these 5 steps for the remainder of our semester here. So again, step 2 now, you have the complete package. You have everything, all the steps you can do now on your own. And importantly, just remember, you need to figure out your comparison distributions characteristics. And we mentioned this before, I'll mention it one more time. Be very careful on this because we now have 3 separate distributions that could be mentioned in a question. And all 3 of these distributions have means and they have standard deviations. So make sure, take a second, make sure that you're dealing with and getting the correct information. So your descriptions, your questions will say things like, the population mean is this. The sample mean is this. Know which mean you need to grab. Was it the sample mean or the population mean? It's your population mean to figure out your comparison distribution. It's the population mean that you need for your comparison distribution. And then this standard error of the mean, your standard deviation of your comparison distribution. Once again, grab that population standard deviation, but now you have to divide it by the size of your sample. So it's a combination of a little bit from your population, a little bit of information from your sample, but do make sure that you're doing that step. Because again, what I find when students make errors on this stage of the course, what they're doing is they are grabbing their population mean and their population standard deviation and using that as their comparison distribution, and that is incorrect, and that is not allowed, and that can lead to an incorrect conclusion, which is something that we absolutely cannot tolerate when we're dealing with the lives of individuals. All right, so that is it for today's class. So just a reminder, the MyStatLab study plan probably going to become much more important as we move forward. So if you're not getting 100% on your pretest, do give them a try. It's very important that you give them a try. That has been shown to, again, increase learning outcomes later on. But I definitely do not want you spending hours and hours on the pretest. That could be better spent doing other things. So give it your best attempt. Try it a couple of times, but if it's not working out, just know that you can complete the study lab points for each chapter to earn 100% on those pretests. And you are now ready, if my PowerPoint will ever get there, you are now ready for assignment number 9. Chapter 6 that's due tomorrow by midnight. And we got about 20 minutes left, so if you want to start on that homework right now, if anybody has any other questions, let me know. And we'll devote the rest of today to practice time. Yep. Sorry? Oh, okay. So this is chapter 8?
Yeah, the pretest.
Oh, okay, yeah. All right, yeah, no, we can talk about that. So, chapter 8, not to give too much away, because I don't want to bombard everyone here with too much info. Chapter 8 gets us to our first, honest to goodness, you will encounter this over and over again, segment of statistics. So up until now, we've been dealing with a very artificial situation. We've been dealing with a situation where we know the population. So you'll notice that this entire time that we have been talking about hypothesis tests, somehow, mysteriously, you have had access to the population information, right? We've been, oh, here's your population mean, here's your population standard deviation. And we also mentioned that that rarely, if ever, happens in the real world. So what happens when you don't have access to your population information, but you still want to do a hypothesis test? Well, what they do is you use your sample to estimate your population. So the big move in chapter 8 is when we are dealing with a population and we have no idea what its standard deviation is. How are we going to get our distribution of sample means? How are we going to get our comparison distribution if we need to take this number, this spread, and divide it by the square root of the size of our sample? How are we going to get this number? So what chapter 8 does is it says, well, we don't know anything about the population, but we do have this sample that we took, and the sample's from the same population, and we can measure the sample's standard deviation. Whoops. We can measure the sample's standard deviation. So let's say that we know the sample's standard deviation, and it's 100. Let's just use that to stand in for the population standard deviation, right? So that's the move that occurs in chapter 8. You can do that move, but you can no longer use the unit normal distribution table. You can no longer use the z-scores, or that z-distribution that we've been looking at. You can no longer flip to table A1. That's why there's table A2. So, for reasons that we'll get into next class, this distribution here, where you estimate your comparison distribution based on your samples, your sample standard deviation, that distribution kind of looks like a normal curve, but it's not exactly a normal curve, which is why we have table A2, and this is called a t-distribution rather than a z-distribution. So that's why we have the new table. So you got to go to the new table for chapter 8. The second thing is how to read this table. And for that, you basically zoom in on the information that you need by taking 3 pieces of information to get to that one number that you're looking for. So the first thing you want to know is, are you doing a one-tailed or a two-tailed test? Because you'll see that half of this table over here is for one-tailed tests. Half of the table over here is for two-tailed tests. So that's the first thing you got to ask yourself. So let's say that you're doing a two-tailed test. That's the area of the table you're looking for. The next piece of information that you need is you need to know your degrees of freedom. How many degrees of freedom do you have? And your degrees of freedom is the size of your sample minus 1 for this first chapter. So the degrees of freedom, if you have 9 subjects in your experiment, your degrees of freedom are going to be 8. So now you're looking at this row right here. So we're in this half, we're in this row, so it's one of these 3 numbers. And then the last thing we need to know is what is our alpha value? And that tells us which column to look in. So if we're dealing with an alpha value of 0.05, you basically look where all of that information intersects, and that's your cutoff score.
So the alpha value is the significance level.
Yes.
Correct.
Mm-hmm.
And then our sample is going to be the number of different scores in sample?
Yes, it'll be your sample size.
Okay.
Your sample size is
Right.
how many scores do you
So
have?
that would be, on this one, it's 27, so just 27 minus 1?
Would be your degrees of freedom.
Okay.
Yep. And this is going to be your first realistic or super realistic hypothesis testing chapter, because again, this is one where we know nothing about the population. So that occurs most of the time. It's very rare that somebody will be doing a study specifically on IQ scores, where you know in the population the mean is 100 and the standard deviation is 15. Right? It's going to be very rare that somebody's doing a psychological study on the heights of people in our population, where you know that the mean is, well, I don't have that data on the top of my head, but you know there's a certain mean, there's a certain standard deviation because enough people have been measured. Usually you're dealing with things where you don't know the population, but you always have a sample. And the move here in Chapter 8 is to take that sample and use the information about the sample to estimate stuff about your population. But as soon as you do that, you got to go to table A2. You got to go to that T distribution rather than the Z distribution.
Well, it tells you scale of 1, right?
It has to be somewhere in
Is that what that
the
means?
question. You see?
Well, I guess that's where I'm confused on how I'm
Yep.
reading it.
So tails, 1 tail, 2 tails. High predicted means you want the positive high side.
Okay,
Low
so
predicted
this is
means you want the
saying
low side.
A is 1 tail, B is 2 tails, C
Yes.
is 1 tail.
Mhm.
Okay, so then, and that tells you that your alpha level is 1, so does that mean I'm looking right here?
Yeah. So that's just again, you can settle right there. So depending upon, so that 0.01
Mm-hmm.
would be that column. Right there.
Okay.
1 tail, you're over here.
Right, this one says 1 tail,
Yep.
so I'm looking
So
right
you're
here.
here, you're in that.
This one?
Yep, and then you gotta find your degree of freedom, which is 1
Which
less
looks like
than the size of your
26.
sample. Yes, it would be 26.
But I don't see 26. How do you do that?
You might have to go to the next page.
Perfect. So,
There you go.
you don't say 26. Like, am I moving like, oh, I'm looking at this. Okay.
Because that's your degrees, so the DF is your degrees of freedom.
So that means my final score would be 2.4.
Yep. 2.67.
Okay.
So that is a preview of what we're doing in that class.
I just got confused.
Yeah, no, it's what you're going to find that we're going to be doing for the rest of this semester is basically the 5 steps are going to be exactly the same. We're going to keep doing those 5 steps, but we're going to make small little changes depending upon the situation. So for this one here, we're going to do the real life studies where you have one sample and you're comparing them to some value, right? You're comparing them to some amount. So if something is like, oh, you have a GPA of 3.5 to get into this university, we'll compare a sample to a GPA of 3.5, right? So we know what we're comparing it to. And then later on, we'll see what you do when you have 2 samples. One of them's treated and one of them's not treated, and you compare the 2 samples. And then the last part, we'll say, well, what if you have 3 or more samples? What if you want to know about young children, teenagers, and adults? Like, how do you do that comparison? So it's always the 5 steps, but we just kind of keep building in terms of here's what you can do in this particular situation.